Hi everyone, I'm Giacomo Delia and this video is for the last experimental activity together. Today we're going to talk about multi-axial environmental vibration control testing by exploiting our three-axial shaker that you can see here behind me. We will use three different vibration control techniques, so mime random, mime sweep sign and the TWR, the time waveform replicator of SimCenter test lab. So this is our three-axial electrodynamic shaker by Dongling. Dongling is a Chinese manufacturer. It is one of the largest shaker manufacturers in the world. Dongling have already sold several 3D shakers in Asia and US, but this one is the first here in Europe, and therefore we are very lucky and proud to work with such as avant-garde test facility. This excitation system adopts an hydraulic orthogonal decoupling bearing units for connecting three independent shakers of 10 kilonewton each. So this one, that one, and that one. Behind we have an oil pump which pumps high pressure oil inside the bearing units in order to avoid the metal-to-metal contact and to guarantee the excitation along the three orthogonal directions simultaneously. This bearing units is a patent by Dongling, and it is the main characteristic, innovative characteristic of this kind of shaker. The frequency range is up to 2 kilohertz, and the maximum payload is 100 kilogram. These three shakers are air-cooled. We have three big fans outside the laboratories that exchange air with the shaker through these cooling tubes here. And the three shakers are connected with three independent amplifiers. Each amplifier has an integrated computer assistant with a touchscreen display that allows you to control the power of the fans, the stop of the machines, or set several operating characteristics and performances of the shaker. The amplifiers are connected via VLC cable into the SCADAs. This is our data acquisition hardware, the SCADAS mobile, that is made up of the VU8 input and the DAC4 output modules. The DAC4 module is the one that allows to feedback control the shaker and therefore is critical for the vibration control testing. This SCADAS is connected with the computer through this Ethernet cable, and then we have also two three-axial accelerometer here connected into the SCADAS. The first one here is the control one and is fixed on top of the head expander. This is the head expander. It is a magnesium table of 15 by 15 50 by 50 centimeters and more or less 15 kilograms. The second accelerometer, three-axial accelerometer, is this one. Is the measurement one that is fixed on the test basement. This is an exhaust gas recirculation valve, so an EGR valve of a Maserati car. And that's all about the test equipment and all the sensors for this activity. So now I switch on the shaker and I'm gonna go to the computer just to show you how to perform a vibration control test. We will start with mime random, then we will skip on TWR control technique. We will perform the same vibration control test. Of course, with mime random, we will define the test specifications in frequency domain, so the PSD and the TSD of our control accelerometer. Instead, in the TWR, we will define the test specification directly in time domain. At the end, we will compare the result for the measurement accelerometer, comparing the two vibration control technique, and we will skip on MIMO's with sine, just to show you how to perform a sine sweep by using 3 control direction simultaneously. Okay, now we are in MIMO random control, one of the possible software solutions for environmental testing available in SimCenter Test Lab. I switch on the shaker, so probably you can hear some background noise, but unfortunately the shaker, the fans and all the stuff here are very noisy, and so I mean I try to speak as loud as possible. So let's start. Here, as always, we have our flow chart here in the bottom with all the section that we have to follow for performing the test. Now we are in the navigator, the main section. Then we will skip on the channel setup section to define the channel setup parameter, and then here in the MIMO random setup section, where we can define the control parameter. We define our test specification, the data acquisition setting, and so on. And then there is the system identification section. This section is a critical pre-phase test, because during this phase we will estimate the transfer function between the inputs and the output of our control system, therefore between the shaker drives and the channels of our control accelerometer. Then when we have identified our system, we will check all the control parameter here in the system verification section, and then of course if everything will be okay, we will perform the control test and all our measurements here in MIMO random control. So let's start and click here on channel setup. You perfectly know this worksheet, so I don't spend much time here to repeat again the same stuff. Anyway, as always, you have to set the parameters of our 2 triaxial accelerometers. As you can see here in the channel group, you can choose between control or measure. So we have in the first 3 channels the one of the control accelerometer that I call 1 here in the point name box. Then we have to define the direction of our accelerometer with respect to the global coordinate system, then the ICP mode, and then the actual sensitivity that of course you can find the data card of the accelerometer. The same for the second accelerometer. In this case it is a measure accelerometer. The name is 2 with the corresponding direction and of course the ICP mode and the actual sensitivity. Okay, so here the only thing that has changed from the previous video is that you have to define if a channel is a control or measure channel, and that's it. Therefore we can directly move on in the MIMO random setup section. Here we have to define all the control parameters for the analysis. First of all, we activate our 3 shakers here. We put the direction, so plus X, Y, and Z, and we set the maximum level. We can put 8 volt. Our shakers combined with our SCADAs, the maximum level is 10 volt. 8 volt is a good data for safety reason. And then we can skip here on the right just to set some acquisition parameters. Here in the control panel we can set the frequency resolution, probably 1.5 Hz is okay, and then by setting the minimum frequency and the maximum frequency we set the frequency range. So here from 10 Hz to 500. Of course, the software automatically change the minimum and the maximum frequency depending on the frequency resolution, the delta F that we have imposed. And then we can skip on into the safety panel here. We got the RMS abort. Probably to better understand what these values mean is better to define the our test specification first. So here in the reference profiles panel, we have to define our test specification. This that you can see here is the spectral density matrix. It is the global control target. Our control channel are three, the three direction of the control accelerometer 1. So along the diagonal of this matrix, you have to define the PSD profile that you want to replicate along the X direction, along the Y direction, and along the Z direction of the control accelerometer. And then, of course, we have also to define the correlation between each control channel by defining the phase and the coherences of the GSD, so the off-diagonal term of our matrix. As you know, our control target is a symmetric matrix by definition, and therefore we can just define the upper triangular part for defining the entire control matrix. So we click here in the first element and then in edit PSD profile just to define the PSD along the X direction. Here in the frequency we write 9 and 500, and then here in the amplitude we have to set the amplitude PSD, of course in G squared per hertz. So we can put 1 and 1 because we want to just a flat PSD in the entire frequency band. And then here in the global scaling we can scale down our PSD profile by setting the proper RMS values. So if I put 1G RMS and I click OK, now if I put the limits optimized, okay, you can see that I have created a flat PSD profile from 9.38 Hz to 500 Hz. As you can see, we have the green line here, that is our reference, so the profile that we want to replicate during the test. And then we have also other lines, these two that are the the upper and this one the lower alarm threshold, and this and this one in red, that is the upper and lower abort threshold. As you can see, if I click on edit PSD profile again, Tesla by default set the upper and the lower alarm at minus and plus 6 dB from the reference, and the upper and lower abort threshold at minus and plus 6 dB from the reference. That basically are the limits also suggested by the standard when performing this kind of test. So I click on OK, and now we have our first test specification for the channel X. Now for the second test specification, I want to replicate a Y pink noise PSD profile. So I click here, then in edit PSD profile. So as a frequency I put 9 and 100, then as amplitude 1 and 1, and then in the right slope minus 6 dB per octave, and then I can rescale down my profile with 1G RMS. And as you can see, we have the typical profile of white pink noise. So white noise, a flat PSD profile till 100
Hertz, okay, and then pink noise still 500 with minus 6 dB per octave as a slope. I click OK, and then we define the last test specification along the Z direction. We can do this one as, I mean, a blue-white noise. So edit PSD profile from 100 to 500. I set 1 and 1, and then in this case left slope plus 6 dB. Okay, I rescale my PSD profile with 1G RMS. This is a typical blue white noise PSD profile, so increase till 100 Hz and then flat PSD. So now we have our three test specifications along the three direction. So flat profile along the Y direction, then a white pink noise in the Y direction, and the blue white noise along the Z direction. To complete our control target, we have also to define the coherence, so the correlation between each control channel. For this test, we can put high coherence between all the control channels, so like this. Now we have fully defined our control metrics, okay? And we can skip again on the right just to define the remaining parameters. So here in the safety panel, we have the RMS abort, 3 dB, it's okay. It means that if during the control test, the measured PSD profile exceed 3 dB with respect the reference RMS value, so 1G RMS, the test will be stopped. Then we have the maximum alarm and the maximum abort lines. We can put 150. That means if during the actual test more than 100 or 50 spectral line exceed the alarm or the abort thresholds, the test will be stopped. And then we can deactivate the repeat aborts, and we can move here in the schedule panel. We have to define the startup level, the number of steps, equalization times, and the full level time. We can put as a startup level minus 6 dB, number of steps 2, then equalization time 10 seconds is okay, and the full level we can put 40 second. Okay, this setting means that we will perform the full level control test for 40 seconds, okay, but we will reach this level starting from minus 6 dB with the first step for 10 seconds. Then we will increase the level up to minus 3 dB for other 10 seconds, and then we will reach the full level. Okay, this is just for safety reason, because typically you don't know exactly if the setting that you put here are correctly for your test spacement or your test equipment and so on, and therefore it's better to reach the full level starting from low level and increase step by step. Okay, now we can activate our throughput recording, and with the memorandum setup section we have done everything, so we can go into the system identification setup. As explained before, in this section we have to estimate the transfer function between the inputs and the outputs. So between the drive signal of the shaker and our control channels. This is a critical and fundamental pre-test phase for any vibration control test, because without the a priori knowledge of the relationship between the inputs and the output, the control algorithm cannot define the proper drive signal to be sent to the shaker during the control test for replicating our test specification. So to do that, we will excite the structure by using decorrelated white noise random signal, and we will measure the responses in all the channels, and of course estimate the transfer function. Here on the right, we have just to set up the number of averages in order to estimate a correct transfer function. So maybe 10 is okay. Pseudo-random and random as search parameter are okay. And now I arm the shaker. Here can skip, okay. So I click on start. Now the shaker is running. So here if I change, okay. This plot here are the drive signals. So random signal. If I switch on PSD, as you can see, are flat PSD, so white noise. And here you can see our responses in terms of PSD or FRF. Okay, the transfer function between the drive signals and our control channels. So now that we have estimated the transfer function, we can skip on the system verification section. In this section, we have to verify the data before to run the control test. So if I click on calculate, here we are in the summary subsection. So in the responses panel here, you can see the RMS level of our control channels. So 1G RMS is the value that we have required in the MIMO random setup. Okay. Instead, in the drive panel here, the software say to you the power required by the shakers in order to replicate the test specification. Okay, so the status here are okay for all the shakers. Otherwise, here could appear a warning message, an error message that say to you the required power is higher than the capability of our shakers, and therefore you have to rescale down probably your test specification. Okay, now if I click on inverse FRF and I plot all the impedance of our control system, okay, as you can see here at this frequency, there are some peaks that probably is an anti-resonance of our structure. If I click on drive, of course, we have at the same frequency the same peak, because I mean when you have an anti-resonance like this, it means that your structure responds with a low level, and therefore your drives have to push to high level voltage in order to reach the test specification. Okay, this will probably cause some problems during the control test. Maybe we will not see a perfect control replication of our target. Anyway, here in the summary, all the status are okay, so we can move into the MIMO random control section. And here we can run our control test. So as run name MIMO random, it's okay, so I can click on arm to arm the shaker. Now just a second, we have here our control channels, so the flat PSD along the X direction, the white pink noise PSD along the Y direction, and the blue white noise PSD along the Z direction. As you remember, our test start from -6 dB for the first step, then skip on -3 dB, and then to full level. So we can click on start. Now the shaker is running. We are at minus 6 dB, okay, for 10 seconds. Now we are in minus 3 dB for other 10 seconds. And then full level, 0 dB. Okay, here you can see the measured PSD along the three control channels. Now we are in the closed loop, so the control algorithm calculate the error between the measured and the reference PSD and try to reduce the error and try to, to reach our control target. Okay, 40 seconds for the full level, and we have done our control test. Here you can see that just 4 spectral lines have exceeded the alarm thresholds, and 0 are the spectral lines that have exceeded the abort threshold. Okay, therefore our test is a normal end control test, and of course we can skip on the navigator just to show the control result. Here in memorandum we have our data of the control test. So in outer loop, PSD, control, we have our PSD, so we can plot them. Okay, so the X direction, the flat PSD, the Y direction, white pink noise PSD, and the Z direction with the blue white noise PSD. As you can see, we have obtained very good control result. Just probably here is the same frequency, more or less 240. Just to check, yes, it's the same frequency where we have the anti-resonance of our system, and as I explained before, we have obtained not a good control result here. Then we also can plot the result in the measurement accelerometer. Okay, so accelerometer 2, X, Y, and Z. If I skip to amplitude, okay, probably here we have a resonance of our EGR valve at 170 Hertz. Okay, and then we can also plot the throughput data. Okay, these are the time recording of our control channel during the control test. What I want to do now is to take this time recording and try to replicate this time history into the TWR software, just to try to control them and try to check if we obtain the same result here in the measurement accelerometer. Okay.